Okay, so today's video is all about the topic of, well, if I have that open, of gravitational energy. So gravitational potential energy, and how much energy do you need to leave the Earth? So let's deal with how we define gravitational potential energy, and what we mean. So if we've got an object of mass m, that's our planet, and what we want to do is to essentially, have a situation where we can leave our planet and never come back. Now that turns out to be a little bit sort of complicated. We can't simply use, we can't simply use the equation GPE equals mgh. We can't use this equation if we start leaving the surface of the planet by some kind of noticeable distance, because this gravitational, that g, is not constant as r increases. So we have to actually be starting to use form equations that enable us to deal with the fact that the gravitational field strength is going to change as we move away and outwards. So what we're going to do is we're going to define a term of what do we need to do if we want to move an object to various distances. And what we will talk about is the gravitational potential energy is going to be defined as the energy required to move an object not from the surface of the planet, to a distance r, but from infinity to a distance r. How much work is done going from here to here? Now that sounds somewhat counterintuitive, but there's a reason for that. Every planet that you stand on will have its own unique gravitational field strength on the surface of that planet, which means that if you start from considering that zero energy is when you're standing on a surface, once you go to a different planet with a different surface and a different gravitational field strength, your concept of zero changes. So instead what we do is we start with zero being over here, infinitely far away, and anything that is infinitely far away has zero gravitational potential energy. But as you get closer, you get negative. So the values of your gravitational potential energy, if you are anywhere less than infinitely far away, is negative. Okay, so gravitational potential energy is the work done moving an object of mass m from infinity to a distance r. Now, because of the conservation of energy, if it's a certain amount of energy to do that, then it's exactly the same amount of energy to go back again. So if you work out the gravitational potential energy that you sort of lose, for want of a better word, by falling from zero to this negative number at this distance, it's the same amount of energy to get back again. So it can tell you, how much energy it takes to escape from a planet and never come back. So, we can start working these things out. So let's see if we can derive what the equation looks like. Now, warning, maths maths is about to occur. Maths is not on the A-level physics specification, but I figured it's nice to show you where the equation that I'm just going to spit out comes from. So let's consider this sort of problem. So we've got, say, the Earth, sorry, not the Earth, a planet, which has a mass of m. We've got a point that's infinitely far away, and we have an object, and that object will have a mass of m, little m. And we're interested basically in, if it comes back down to the planet, how much GPE is it essentially losing, which tells us how much GPE we need to go back. But in order to do that, because the force on it due to gravity is going to change with every little movement, let's instead start with a tiny movement. Okay, let's start with a tiny movement from infinity. Let's move a small amount. Oh, that was not what I wanted to do. Let's have a tiny movement from there to there. Okay, let's move a small amount dr. Okay, so we're going to have a little bit of work done moving from infinity to now a new distance, which was dr away, and we say, okay, we're going to do a little bit of work. Okay, well, what is that little bit of work? Well, the work done by a force moving a distance is the size of the force times by the distance we're going. We're going a little bit of distance. F times dr. So we can then say, right, okay, well, the force is Newton's law of gravity. So the little bit of work we're going to do is minus g m of the planet, m of the object, over r squared dr. That's nice. Now, that means that we can sort of make this a bit neater. For those of you who love integration, you might know what's going to come. Our little bit of work is equal to minus g m 1 over r squared dr. And what we can do is we're going to get the total amount of work. If we want to move a bigger distance, we would just add up all the little individual bits of work, and therefore we would integrate this side as well. And we're going from infinity to some distance r. Okay, now that distance r could be all the way back to the surface of the planet. Could be to here. Could be wherever we want to go. We're going to move from infinity to that distance r. Now, if you integrate that, you end up with minus g m m, and you end up with 1 over r, because you've moved to a distance r away, minus 1 over infinity, because you were from infinitely far away. Oh, look, 1 over infinity is 0. So bye-bye. And there we go. That becomes our equation. We get the work done, okay, is minus g m over r. That is the equation for gravitational potential energy. So the gravitational potential energy of an object at a distance r is minus g m over r. Hurrah! R. Now, let's test that. Let's test that by comparing it to something that we know. So a test of this could be saying, okay, what is the gravitational potential energy that you gain on the Earth if you move from the surface of the Earth and you move a kilometre into the sky. So you move up 1 kilometre. And the important, now if we were doing this by MGH, we would say, oh, let's give this a mass. Let's say it's a 50 kilogram object moving 1 kilometer into the sky. We would get 50 times 9.81 times 1000. And that comes out as being 490,000 joules. That's the GPE that you've gained by going this 1 kilometer into the air. If we're going to use it the more formal way, we're going to use Newton's law of gravity, and we're going to use this version of it. Well, we're still expecting the same number because, well, 1 kilometer isn't very big compared to the radius of the Earth. But let's deal with our calculations. Radius of the Earth is 6,400 meters. The mass of the Earth is 6 times 10 to the 24 kilograms. The mass of the object is 50 kilograms. And the Newton's gravitational constant, G equals 6.67 times 10 to the minus 11. Now, if we think about solving it in this manner, what we could say is that your change in gravitational potential energy is equal to your GPE when you're at the radius of the Earth plus 100 meters minus the GPE when you're just at the radius of the Earth, 1,000 meters, sorry. So, well, let's put that in. So we get, because these are minus signs, we'll get minus GMEMO over 6,400 So essentially what I've done is I've added 1 kilometre to this bit. I've also I've counted the fact that these things are negative. So that becomes a plus actually, because that's a minus, GP is a negative, so that's almost become over here. That's all that term. I just counted for my negatives there. So what do we get? Well, the nice thing is we can actually take that into two parts. We've got G, M, E, M, O on both sides. So the change in GPE is equal to G, mass of the Earth, mass of the object, 1 over 6,400,000 minus 1 over 6,401,000. Multiplying these through using my calculator, which is 6.67 e to the minus 11. So I get 2 times 10 to the 16, and if I just do this, I get 2.44 times 10 to the minus 11. And after all that work, multiply those together, and we get 490,000 joules. Yay! Obviously, this is not something that you would do if you're not leaving the planet Earth. But let's imagine that we're not. Let's imagine that you're going. Let's say you're going from the orbit of the Earth, and you're trying to send something. So it is, not to the moon. Let's pretend the moon isn't there, but we're trying to send something to a distance of the moon's radius. So we're trying to send it 384,000 kilometers. And we're interested in this case, well, this becomes a slightly more different thing. So let's not pretend, let's ignore the moon's pull itself, because that's going to, and then at certain points, let's say we're saying to the other side of the moon. So what we get is this would still be the same, this 2 times 10 to the 16, because same object, a 50 kilogram object, but this becomes a very different sort of sum. This is still the radius of the Earth, but now we've got 384,000 kilometers. So we end up with the GPE that you gain to send something, turn this 50 kilogram object to the moon, is 2 times 10 to the 16. And then we've got 1 over 640000 minus 1 over 384,000 kilometers, 384,000 kilometers. So we have that, and this term this time is a little bit, is going to be somewhat different. So 1 over 2. So this becomes 1.54 times 10 to the minus 7 times 2 e to 16. And so this time, what we need there is 3.07 times 10 to the 9 joules. So that is obviously a lot more energy to send something from the surface of the Earth to the distance away that the moon is. Now, as we, I don't know why I'm rubbing that up, don't need to do that. So this is if we're dealing with larger objects, we need to worry about that kind of size. We need to use this equation. We can't use MGH, because MGH would have just predicted something ridiculous. We'd have got, let's just check this, MGH, we'd have ended up with 50 times 9.81 times a change in height, which is 384,000 minus times 50 times 9.81. Yeah, it would have assumed 1.85 times 10 to the 11 joules, which is, very big. That's a lot bigger. So it's wrong by quite some order of magnitude. So that's when we have to start using it. So that's the power of that equation. Let's define the sort of second thing that we can work out with this, which is, let's go back to this idea of what we call the escape velocity. So the escape velocity is defined as the speed you need, the velocity you need in order to be able to leave the surface of the planet, and never come back. You would travel away forever. Okay, so what is the escape velocity on the Earth? Well, what we can do is we can say, let's give our person. Did we start the image up at the top? Yay! Okay, there's no wrong one. Here we go. So let's say we've got someone that we don't really like very much. I'm going to give them a different mass this time. I'm going to give them a mass of 80 kilograms. And we're trying to move them from here all the way up to there. So we're trying to pacow, and they just never come back to us. So what we can do there is we can look at what this means. So given that we're moving something, so we've got our change in GPE, okay. Well, we're going from what we're doing is we need to know the difference in the GPE at the Earth to the GPE when we are infinitely far away. And we've said that this is 0, this term is 0. So what we actually just need to do that is the change in GPE is just, because it's defined from this, is we need that as G M M over R. We need to give the object this amount of energy in order to leave and never come back. So if we take our person, and let's say they're 80, well, actually, no, let's say they are still 50 kilograms. So let's say it's a 50 kilogram person and not a 50 kilogram sort of satellite. What we can do is we can say, okay, so that means 6.67 times 10 to the minus 11 times 6 times 10 to the 24 times 50 kilograms to the person over, in this case, the radius of the Earth. Okay, and what do we get? Well, in this case, we get 3.1 megajoules. Now, what's interesting is that's actually not too much more than we needed to escape to get to the moon. Okay, to get to the moon, you've got to give someone nearly as much energy. You have to get, to get sort of to infinity, and that's partly because, remember, the force of gravity is dropping off by 1 over r squared, and so it starts very rapidly having an influence. So we need 3.1 megajoules of energy. What does that mean in terms of someone's velocity if they want to have 3.1 megajoules of energy? Well, that is half mv squared is equal to 3.1 times 10 to the 6. We do our things, so that gives us v, don't need v squared. V is equal to the square root of 3.1 times 10 to the 6 times 2 over the mass of the person, which is 50. And what that gives us is an escape velocity of about 11 kilometers per second. That is how fast you need to throw this 50 kilogram person in order for them to leave the surface of the Earth, travel off into space, and never come back. They will constantly be traveling away. Eventually, when they are infinitely far away, they will have zero energy and stop moving. But the thing about infinity, it's hard to get to. So that's called the escape velocity. Now, what's wonderful, and it does happen as a result of the fact that we're dealing with gravity and it's related on the mass of both objects. If we actually look at that more formally, is that to escape, you need a kinetic energy half mv squared equal to gmm over r. And because you've got a little mass in both, the mass of the object, well, that's going to cancel out. And that means that the escape velocity is not dependent in any way, shape or form on the mass of the object you're trying to launch away. The challenge is, obviously for us, it's harder to accelerate a more massive object to a certain velocity, to 11 kilometers per second, but the speed you need to reach, the velocity you need to reach if you're standing on the Earth's surface is not any greater. But what you end up with is that v is equal to the square root of 2gm over r. And that right there is the second of the kind of key equations that we have. So we have an equation for the gravitational potential energy of an object at a certain distance r, which is how much work it needs to do to get to infinity, or from infinity, and then we have the escape velocity, which is root 2 gm over r. So, next thing to define is what we call the gravitational potential. And this is where we imagine that the field is there, that the gravitational field strength is there, but we haven't put an actual mass there. So it's what would be there per unit mass. So this is a defined thing. This has got a symbol of Vg. Okay, and this is defined as the work done per unit mass to move an object from infinity to a distance r from a body. And because it's the work done per unit mass and the work done is the GPE, what we end up with is that the gravitational potential is GPE over m. So what you end up with is minus gm over r. And so you can work in terms of the gravitational potential, which is the change in potential energy per kilogram as you move to different distances away from another body. And so those are the different sort of like relationships we have. We have gravitational potential and gravitational potential energy. Those two equations, using them, work pretty much in exactly the same way. It's just one you've multiplied by the mass of the object you're moving. And then we've got the escape velocity of a body, which is the square root of 2 gm over r. And those two things, those things combined, is what teaches about gravitational potential and potential energy and how we solve problems with them. So, there we go. Smiley face.